All right, so here we go. So I've got us going here. So work and energy. Chapter 6, like I said, it's going to be Chapter 6, skipping Chapter 5. Here we've got a baseball player. Work and energy is actually force times displacement. So that's why we've got this picture of the baseball player. So what matters in terms of the work done onto the baseball in this case is going to be his force that he's applying. Let's assume for a moment that the force that he applies is a constant force throughout the displacement that he applies. I'm going to go over this same scenario in two different ways. I'm going to talk about this scenario now in terms of work and energy. I'm going to also talk about this exact same scenario in the next chapter, which will be momentum, because we're going to talk about the term impulse. So keep it in mind, because we'll talk about the same event, just talking about it in a different way. So with that, he's applying a force over the course of a distance, right? So I'm assuming that the baseball player is only so strong. So he's going to apply whatever maximum force he can apply. So why is it that he reaches back so far? So he reaches back as far as he can, right? If you ever watch a baseball player, a little kid will start from like his shoulder or something and just try and throw, and it doesn't go very well. Versus somebody who's an experienced person at throwing, they're going to reach way back. They're going to step forward as much as they can, and they're going to be in contact with the ball for as long of a period of time as they can. And in this case, I'm going to describe it in terms of him being in contact with as long of a distance as he can, because whatever maximum force he's got times the maximum distance he can apply gives you the most amount of work he can apply to the ball, and that work translates directly into the change in energy of the ball. In fact, that is the definition of the two and how they relate. Work is equal to the change in energy. So we're going to work about the work done, the kinetic and potential energies, mechanical energy. Mechanical energy refers to basically the energies that you can see, things that are not thermal energy. And so we're going to talk about conservative and non-conservative forces. When is it conserved? When is it not conserved? And we will talk about power. Work is equal to force times displacement. The reason why they put cosine theta in here is it's known as a dot product. If you want to know more about that, you can look up Khan Academy video on cross products versus dot products. So a dot product basically means that you are looking at the angle between these two and taking the cosine of them. Basically what it comes down to is this. Here's the bottom line. You don't need to worry about what a dot product really is, to be honest. What really matters is this. I actually prefer to take cosine theta out, all right? Because I want you guys to actually actively think about what's happening here. Work is force times distance, or displacement. But, there's a big but, the work done only applies to the force that is in the same direction as the displacement. So in this case, even though the person is pulling up at some angle, so this person is pulling up some angle theta, the x component of that force is the only part of the force that is in the same direction as the displacement. So we can look at it in one of two ways. You can either look at it in terms of the x component of the force times the displacement, or I can look at it in terms of the amount of displacement that is in the same direction as the force. So it winds up being the same thing. It's the angle, it's the cosine of the angle between the two. And in fact, what if I, just for the purposes of diagramming it a little bit better, so we've got our, let's make a box. Got a box. I've got a 4. I almost did that right. There, I feel better now. So we're going to drag the box across the floor. We're going to apply it at some angle theta relative to the horizontal. So it's going to go in that direction. That's going to be the delta x, and this is going to be the force. So we've got an x component of the force and a y component of the force. So the y component of the force, right, the force in the y direction, is going to unweight this box at least a little bit. So it's actually going to decrease the friction force. So it doesn't mean that it's completely wasted, but it doesn't apply towards doing the work. It's only the force that is in the x direction that actually goes towards the work. So in this case, I'm going to say that the work is going to be equal to the force in the x direction times delta x. And like we were just saying, the work is going to be equal to the force times cosine theta, delta x in this case. Right? It doesn't matter if cosine theta is after the x or before it. It doesn't matter. It's all the same because you're multiplying by cosine theta. Fair enough? It's only the force that is being applied in that direction that actually goes towards doing the work. Oops. All right. All right, so here's a really classic sort of example of how we can apply some of this stuff. If you've got some guy who's walking across, let's assume for a moment that he has already done any acceleration, that he is moving with a constant velocity. Okay, I want to be clear about that. He's not moving very fast. He's already taken this step, that first step in which he accelerates. He's already taken that one step where he accelerates. Now he's moving at a constant velocity, right? He's moving at a constant velocity, carrying a bag of groceries. How much work is he doing to carry that bag of groceries across the room? He's already accelerated. He's now moving at constant velocity. How much work is being done to carry those groceries across the room? You got to think about that. Yeah, no work is done because there is no net force. Actually, I shouldn't even necessarily say that. There is no force in the direction of motion. There is no force in the direction of motion, so therefore, no work is being done. All of the force that's being applied is in the up direction from him. And since that's equal and opposite to the force of gravity, the bag of groceries are not accelerating up or down, so therefore no work is being done in the vertical direction, and no work is being done in the horizontal direction either. It actually says there's no work done on it, so it wasn't exactly the hardest thing to figure out there. Does that make sense? So here's the problem, is that people often get confused between the concepts of effort versus work. You know, if I can hold something fairly heavy and hold it out somewhere far away from my body, let's see if I can actually do that. It's a lot of effort to hold something far away from your body like that, right? But I'm not doing any work. And just because you are moving does not mean that work is being done. So if I were to ride the skateboard across the room, holding some object, yes, I'm applying a force. Yes, I'm moving. Am I doing work? Work is not being done just simply by going across the room. So 1 joule of work, so these are the units, 1 joule of work is the same thing as 1 Newton meter. 1 Newton meter is the same thing as 1 joule of work. In fact, the unit for energy is the same unit. the unit for energy is the same. It is also measured in joules, not calories. That's used in chemistry. Joule is actually an SI unit for work and energy. So same stuff as before. We're going to draw our free body diagrams. We're going to choose a coordinate system, and we're going to apply Newton's laws. We just now need to look at the displacement that is done to figure out the work done. So here's something to think about. In the same regard, think about the forces that are in the direction of motion. So for something that is in circular motion, which I know that we skipped a chapter, so this will make sense though still conceptually. For something like the moon, its velocity is moving along the tangent here, along the green arrow. That's the direction of its velocity. However, there is no force acting in that direction whatsoever. The only force acting on something that is in orbit, like the moon, is going to be a force acting directly towards the center of the circle. They are perpendicular to each other, which means no work is being done on the moon. The moon is not doing work. No work is being done on the moon. They're at 90 degrees to each other. There is basically no force in the direction of its velocity, at least on average. I say that because in truth, in full truth, the moon is not a consistent distance away from the Earth. There's points in times during its orbit when it's a little bit farther, and points in time when it's a little bit closer. So there's some negative work being done and some positive work being done throughout the month. But by the time it recycles again and gets back to relatively the same spot, there's no work being done. Okay, so if we have a varying force, finding the amount of work done would be a little bit more difficult. Most of the circumstances in which we're going to look at, the force will be constant, but you should understand the concept here on how to find the work done with a varying force. And in fact, we may very well be doing a lab in which we'll need to do this. So just like what we've discussed before, if we were to make a graph where we graph something that's on the y-axis versus the x-axis, and we have a formula in which those two things multiplied gives us what we're looking for, then the area underneath the line gives us, in this case, work. So on the y-axis we have the force, which is changing. We have a displacement, or a distance, which is changing, so therefore displacement. And the area underneath the line will give us our work done. So conceptually, what you can do is if you wanted to estimate it, you can take equal intervals of distance and make these squares underneath the line to best estimate the area total of all of that sections. And then those of you who are in calculus, is this starting to look familiar in calculus yet? Who's in calculus? Have you guys covered integrals yet?
No.
That's what that is.
Last year.
I'm cheating. Okay, it's an integral. Okay, but obviously you get way into it in calc, right?
Mm-hmm.
Okay, but that's the purpose of an integral, is to do just that. As the force changes, you can very accurately get into all the nooks and crannies underneath that line. Is basically what calc does. Any relatively straightforward textbook, simple ending textbook is going to say that energy is the something that has energy has the ability to do work. They're saying that this is technically not true, but it kind of is. I mean, the definition still works at a very fundamental level. So mechanical energy, as I said, is basically the sort of the energies that you can see. It's the translational energy, it's the potential energy. We can look at gravitational potential, elastic potential, chemical potential, and kinetic energy, meaning the energy within a moving object. Thermal energy is not mechanical, nor is nuclear. All right, so basically what's here in the shaded portion is what I want to concentrate on at the moment. Kinetic energy, okay, KE, or a capital K. Oftentimes it's just a capital K, and in fact on the AP test, they simply just use a capital K to denote kinetic energy. I personally write KE just to keep consistent with the text. So kinetic energy is equal to 1/2 mv squared. Now, what they're expressing here, I'm sorry, didn't mean to do that. What'd I do? There we go. Okay, so what they are expressing here is that the net work done is equal to the final energy minus the initial energy. Basically, the change in energy. So the work done, the net amount of work done is equal to the change in energy. So delta KE. Basically, W equals delta KE. Might want to make a note of that in that way in your notes, because really that's the way you would structure it on any problem, right? W is equal to delta KE. Okay. Before I move on, I want to tackle a conceptual question here, and I want you to think about it. What is the relationship between velocity of an object and the energy of the object? What is the relationship between an object's velocity and energy, kinetic energy specifically? How about if I restate the question in a different way, a more practical way? You're going down the road at 20 miles per hour. You're in a school zone. You now increase your speed to 40 miles per hour. What has happened to your kinetic energy? You've doubled your speed. Have you doubled your kinetic energy? What is the relationship between those two things? You must be able to identify these sorts of questions. It would be more than double. It would be quadrupled. So if kinetic energy is equal to 1/2 mv squared, I just want to look at the relationship between kinetic energy and velocity. So what I'm going to do is I'm going to kind of cross out the rest of these things and put a proportional to symbol. So kinetic energy is proportional to v squared. So to answer that question, what I can do is put parentheses around the v like this. And I'm going to say I'm going to double the velocity. Now, the velocity must be doubled before the square gets applied, which means that if I double the velocity, that velocity is now going to be squared. Essentially what it comes down to is I can say that this 2 is going to be squared, giving us an increase factor of 4, which means that this would increase a factor of 4, because 2 squared is 4. So whatever I do to my velocity, whatever factor I increase my velocity by, I must square it, and that will be the increase in my factor increase in kinetic energy. So here's the application in the real world. You've got your car, got a fancy red car. Don't make fun of my car. Okay, make fun of my car. All right, so it's going down the road, and you're going at 20 miles per hour down the road in a school zone. Why is it that school zones are so obnoxiously slow? It's because the stopping distance, the distance in which it takes for you to stop, is directly related to the kinetic energy the car has. So by going from 20 miles per hour to 40 miles per hour, your stopping distance doesn't double, it quadruples. It's an exponential increase. So your kinetic energy will exponentially increase with velocity, and so will your stopping distance. So as little Billy runs out in the street chasing after a ball in front of you, he's going to greatly appreciate the fact that you're going 20 rather than something faster. Okay? So keep that in mind. Your stopping distance will exponentially increase with velocity. So as I said, work is equal to the change in kinetic energy. If the work is positive, if the net work is positive, then kinetic energy increases. If the net work is negative, the kinetic energy decreases. So negative work slows something down typically, and positive work speeds something up. All right, really simple example of work being done. So you have a force and a displacement of the nail, so you can talk about how much energy or how much work was done onto the nail. So there's work done from the hammer onto the nail, and that would be measured in joules. All right, potential energy. So there's lots of different types of potential energy. We're going to be looking at gravitational potential energy and elastic potential energy. The elastic potential energy can be, in our circumstances, is typically going to be in a spring. We're not going to look at any specifics of an elastic band. Not anything that needs anything too fundamental there. We're going to look more closely at springs, though, because springs have different characteristics that are easily identifiable. There's spring constants, the stiffness of the spring and that sort of thing. So we're going to look very precisely at that, and we're going to learn how to find what the spring constant is of a spring and things like that. Otherwise, the gravitational potential energy is going to be determined by height off of whatever your zero position is. Typically the ground, but it doesn't have to be actually. Let me say that. Your zero position doesn't have to be the ground, right? So energy is actually fairly relative, especially potential energy. If I have an object at ground level, you would typically consider that to have an energy, a potential energy of 0, right? Can't get it any lower than ground level. Until you then realize that the object is directly next to a cliff or a hole dug to the center of the earth, right? And then all of a sudden you go, oh crap, it can get lower. And then it falls, and now it has negative potential energy, which is okay. It is okay to have a negative energy level. It's all relative, right? So keep that in mind. So again, here in the shaded area, we've got the equation that we are going to focus on, where potential energy, PE, is potential energy in our text. However, in the AP test and the AP equation sheet, they use a capital U instead. They use a capital U for potential energy. Don't ask me why, they just do. Probably because the letter P is used for so many other things. They use something that doesn't have a P. Again, it's all about the work done, so it's cosine theta, where it is the force that is in the same direction as the displacement, or vice versa, in either case. All right, so if you were to raise this object with your hand, you are doing positive work onto the object. By raising it, you are doing positive work onto the object. You are increasing its potential energy. When the object lowers, if you were to lower your hand and the object lowers, it has negative energy. It has negative work done onto it. However, you are not doing that negative work. What is? The Earth, yeah. The Earth is doing that negative work onto the object. So all of the work that you do in this case is positive work. So we're going to do a lab very soon here in which we are going to be determining the amount of positive work that you do. So let's say, for example, you were to work out. You work out. If you do a set of pull-ups, you do 5 pull-ups, the work that you do is going to be only on the way up. Part of the way down is going to be the work done by gravity, and for the purposes of our lab, we're going to ignore that part because that's not work that you are doing. We're going to only look at the work that you do. So MGY or MGH, as you'll see in some textbooks, but MGY is much preferred, as you can understand. So it is gravitational, it is vertical displacement. All right, so we're going to look at a situation with some springs. We have the potential energy of a spring when it's compressed or pulled, stretched, whatever it may be. Some springs don't really have the capability of going one way or the other. But we're going to look at this scenario where, let's say, this is basically what's happening in the projectile launcher that I use, where there's some ball being pressed up against a spring and then it's released. So the amount of potential energy that is in the spring translates into the kinetic energy of the ball. And so the total energy of the system stays the same, assuming that the spring gives off all of its energy to the ball. We can set those equal to each other. And here is that spring constant that I had talked about before. So the force of the spring is equal to negative kx, where k is the spring constant. It is a fundamental value of that particular spring. Not every single spring, okay? Just that particular spring. So the spring constant is different for each individual spring. It's often called the stiffness constant. It refers to how stiff or how rigid the spring is and how difficult it is to move the spring, any displacement. So obviously to find the spring constant would be the force divided by whatever the displacement is. Why is it negative? Well, because I'm assuming that the force applied by the person, if you look at this bottom diagram here, the force applied by the person is going to be to the left, and then the force on the spring is going to be in a negative direction relative to it. So that's why there's a negative there. All right, so just like I had expressed before, where we've got, here we have force versus distance or displacement. The area underneath can give us the work done. The elastic potential energy is equal to 1/2 kx squared, so it's very similar to kinetic energy, where again k is the spring constant, x is the displacement that you pull that spring off of its equilibrium position, off of whatever that relaxed position is. It's where you pull it off from there. All right, let me finish on this. I'm going to say that this is basically a statement of the conservation of energy. I would like to make sure I say this before the end of the class. the sum of all energies at position 1 is going to be equal to the sum of all energies at position 2. So basically what we're saying here is that the kinetic energy at position 1 plus the potential energy at position 1 is equal to the kinetic energy at position 2 plus the potential energy at position 2. So let's say we have a scenario just like that ball that was being pressed up against the spring. In that case, the potential energy would be an elastic potential energy. So I would have the structure, let's say in position 1, its kinetic energy was 0 because the ball wasn't moving yet, and neither is the spring. And then in position 2, the potential energy goes to 0 because the spring has completely transferred all its energy to the ball. So we can say that the 1/2 kx squared at position 1 is equal to the 1/2 mv squared at position 2, and this would be the mass of the ball. So we can basically describe about how the energy is transferred from one object to the other. So the bottom line is that we start here. Okay, for all of our problems, we start here, and then we talk about its transition. All right, so that'll do it. Good start, and then we can start looking at the homework problems. I'm going to have to add more to the questions, but the problems should be set, right?